And welcome to part 2 of our discussion of the two-sample t-test or the independent samples t-test. Now, in our last video I introduced the concept of the two-sample t-test, and we went through an example using that warm-cold embodied cognition study. So I want to talk to you a little bit more about our understanding of what's happening with a study like this. So when we did the warm-cold study, we determined or concluded that the group 1, which had a mean of 4.8, was significantly different from group 2, which had a mean of 3.5. Essentially what we're saying is that those two samples came from different populations. They did not differ just because of chance, that they were actually identical groups, but just individual differences made them different, but rather they came from different populations. In other words, there is one population with some mean, and we drew a sample from that population and we got a sample mean of 4.8. But then we're assuming that there is some other population out there. I guess I better draw it lower. And we drew a sample from that population and got a mean of 3.5. So we are saying then, or we concluded, that our warm group came from a different population than our cold group. There's two completely different distributions there, and that would be our research hypothesis, that our samples came from two different populations. Now, once again, we don't know what the mean of these two samples are, or excuse me, these two populations are. We are estimating them from the samples that we drew, but we don't know what the actual real-world population values are. And because of sampling error, we can't assume that 4.8 is the exact population value, and we can't assume that 3.5 is the exact population value for the cold group. Instead, we're going to assume that it's somewhere near there, based on that concept of the standard error of the difference. But there is a way that we can kind of estimate the actual difference, the real difference between mu1 and mu2, rather than just looking at the difference between sample 1 and sample 2. And this is where the concept of confidence intervals comes in. So let me clear the screen here. All right. What I've just put up on the screen here is the formula that's a little bit different than what you find on the confidence interval slide, and it's different only because I expand the formula for the standard error of the difference between two means. But essentially, what a confidence interval is it will give us an interval, an upper and a lower value, an upper and a lower boundary. And what we're saying is that we are 95% sure that the actual populations that our two samples came from differ by some amount between those two values. Okay, so we're going to get an upper and lower value, which is like our margin for error. We don't know exactly how far apart the true population mu's are, the means are, but we are 95% sure it falls between our high and our low values. So the example from the warm-cold study, if we apply it to this formula, is we first are going to take the difference between our two means. So that'll be 4.8 minus 3.5. And we're going to first add that to the critical t. That's an important thing to remember here. This is the critical t. Critical t. That is the value that you looked up in the t table. Okay, this is not the t that you calculated, it's the t that you looked up at the 0.05 level. If you remember, that was 2.101 from our example. And we multiply that times, hopefully this formula here is looking familiar to you. It is the standard error of the difference between two means. We calculated that when we calculated t. It's that upper part of the t formula. So that value was 0.517 from our previous example. So when we add those together, we get 2.386. Then we do the same thing, but we subtract that difference. So we're going to take 4.8 minus 3.5. That's the difference between the means there. And we're going to subtract 2.101 multiplied by the standard error of the difference between two means. And when we do all of that math, we get 0.214. So our confidence interval of 0.214 to 2.386 says that we are 95% sure that the population of people who rate others while they're warm differs from the population of people who rate others while they're cold by somewhere between 0.2 and 2.3 standard error of the difference between two means, two standard errors. Notice that that difference does not pass through zero. We are 95% sure that the difference is something greater than zero. If the difference was did pass through zero, like for example, one of the calculations came out to be negative. So if we went from negative 0.214 to positive 2.3, that means that zero is a possibility. And if that was the case, we would have our results would have been non-significant if zero was within the realm of possibility. But it was not in our example. There we go. Instead, it was positive. It went from 0.214 to 2.3. So we're saying we're 95% sure that there is a real difference that is not zero between those two populations. So that's what a confidence interval is. It will tell us how far apart we think the actual populations are. If you remember, we're doing inferential statistics. We're trying to infer what the whole population is like, and not just the 10 people who participated in our study, the 10 people who held a cold cup and the 10 people who hold a warm cup, but rather all human beings. And this confidence interval gives us a better idea of where those populations fall. So that concluded our discussion of the two-sample t-test, or the independent samples t-test. So if you're keeping track, we talked about Z, which is used when we have population parameters. We talked about the one-sample t-test, which is used when we have population mu, but we don't have the standard deviation. And then we talked about the two-sample, or the independent samples t-test, where we don't have any population parameters, and we are comparing two independent groups of participants, two samples that are completely unrelated. There's one last type of experimental design that will use a t-test, and this is called the repeated measures or paired samples t-test. And while it's not a part of your homework per se, it is something that you should be aware of because the calculations for it are a little bit different, and there are some certain advantages to using a repeated measures design or a paired samples design. So we're going to talk about that fairly briefly. So in the typical experiment that we've talked about before, we had a sample that we then randomly divided into an experimental group that got our manipulation and a control group that got no manipulation, and then we measured them on our DV and we looked for a difference between the two groups. But the point there is that these two groups are completely separate, completely different or independent groups. There are times, however, when you may want to do something different. You take a sample and you run them through the level of your IV, and after that, excuse me, let me erase that, and then you measure them on the DV. But then you take them and you put them through the other level of your IV and measure them on the DV again. So in this type of design, the same exact group of people received the one level of the IV and the other level of the IV, and you measured them twice. And that's what's called a repeated measures design. Repeated measures because obviously we are measuring the individual on the DV twice under the two conditions that we are examining. So let me give you an example of that. I'm looking at the repeated measures slide on the slides posted online or on the lecture notes. And let me clear this, go to a new page. So as I walk you through the example, I want to first describe what this experiment is about, the one that's described on the slides. And the experiment was testing the Stroop effect. So the Stroop effect actually has, or the Stroop test has two parts to it. The first part is what you see on the left, a list of words, of color words, and the person is supposed to read those words as quickly as they can. So if I read down the columns, I would say red, blue, green, blue, green, red, yellow, blue, green, blue, and so on. And we time how long it takes the person to complete that, just reading the color words. After they finished that, then we show them the second portion, the part that's on the right side of the screen. Same color words, red, blue, green, and so on, but this time each word is printed in a different color ink, and the person's task is to tell me the color of ink that the word was printed in, not what the word reads. So going down that first column, I would have to read blue, green, red, yellow, blue, red, blue, and so on. Now, if you try that yourself, you'll notice it's quite a bit harder to override your brain's desire to read the word and just focus on the color of ink. So the Stroop effect, if I were to test a group of people to see if they demonstrated the Stroop effect, I would give them all just not that sheet, but I would give them all this sheet, time them, how fast it took them to complete an entire page of words like that. And then, oops, I want to clear the ink. And then I would take that sheet away and just give them this page. And once again, have them tell me the color of ink as quickly as they can. So I would end up with 2 scores from each individual. Maybe group one, one person took 40 seconds to read the words, and the person took 1 minute and 12 seconds to read the colors. So I have 2 different scores from each person, and want to calculate, do overall people show a difference in these 2 tasks? So, 2 scores from every individual, and you see some sample data up on the slides, and then the T formula, I'm going to just write it here for speed purposes. So our T for paired samples is the average difference between 2 groups, that's what the D bar is, the mean difference, divided by the standard error of the difference, that's a D. And the standard error of the difference, the formula for that is the square root of the sum of the difference squared divided by n minus the mean difference squared all over n minus 1. Okay, so this symbol S subscript D is that's the actual formula for it. So if you go to the next slide on the lecture notes, I show you what D and D squared is. So for example, subject 1 had a color score, a word score of 22. Why is it not writing? 22, and a color score of 27. So the difference, 22 minus 27, equals -5. Participant number 2 had 27 on the words and 25 on color, and the difference between those is +2, and so on and so forth. If we take the average of those, we sum up the difference scores and divide by the number of scores, we end up with the mean difference. So that's all it is. It's just adding up the differences between each of the paired scores and dividing by the number of pairs that we had. So in the example that you see on the lecture slides, you see that we ended up with a mean difference of negative 4.7. In other words, on average, there was a 4.7 second decrease. Well, I guess you could call it an increase. It took 4.7 seconds more time to read the color of ink than it did to read the words. The second column on that slide is d squared, where we just take each person's difference score, -5 to -9, and so on. I'm reading off of that fourth column on the repeated measures slide. We take that d score and we square it. So -5 squared is 25. 2 squared is 4. -9 squared is 81, and so on. And if we add all of those up, we end up with the sum of differences squared, which was 751. So now we can plug in all the numbers that we have. Oh, incidentally, n was 10. So we can plug in those values to our formula for d. To do that, let's first calculate our standard error of the difference. We're going to take the sum of d squared, 751, divided by n, which was 10, minus the mean of d squared, that's this part of the formula here, and the mean of d was -4.7, but we're going to have to square that, and then we divide that whole thing by 10 minus 1, and take the square root of it, which I know this is getting kind of convoluted here, but that answer is 2.427. That is our standard error of the difference, the bottom half of that t formula. So let me clean up this screen a little bit here. Okay, once again, our t formula is the mean difference divided by the standard error of that difference. We calculated our mean difference to be -4.7, and we calculated our standard error of the difference to be 2.427. So all total, t equals -1.934. All right, and what is this saying? Just like all of the other t and z scores, it says that the average difference between measures of the same individual is 1.934 standard errors of the difference apart. So the t for repeated measures is the exact same concept as all the other t's. It's looking at the difference between two scores expressed in what we would expect by chance alone. That's what the denominator of these formulas is. It's the average amount that we would expect by chance alone. So how do we determine if this is a significant difference? Well, we need our degrees of freedom, which in this case is just simply the number of pairs minus 1. There were 10 pairs of scores, or 10 people minus 1, so degrees of freedom equals 9. And if we look up the critical t in the table, in the back of your book at 9 degrees of freedom, we get that critical t is 1.833. Critical t for 9 degrees of freedom is 1.833. And so now we compare these two. Is 1.934 larger than 1.833. When looking for significance, we don't have to pay attention to the sign. And in this case, yes, it is significant at the 0.05 level. So people who are trying to read the color of ink behave significantly different than when they're just reading the color of words, or not the color of the words, reading the words. It takes them longer. They're behaving differently, and not just because of chance variation. That is a repeated measures t-test in a nutshell, just very quickly. Why would somebody even want to use a repeated measures t-test? Well, your book will go into more details on that, but essentially, by using the exact same group of people, these two groups are identical. The people who read the words and the people who read the colors are identical down to their DNA. So individual differences, what makes me different from you and you different from your neighbor and so on, are eliminated in the research. And that leads to less error. It ends up shrinking the error term, which increases the overall size of t. With a small or less error, it makes it easier to pick up small differences between two populations. So a repeated measures design has that advantage of making it easier to detect small differences because the two groups are identical down to their DNA. The drawback to that is that once a person has been exposed to one level of the dependent variable, you can't unring that bell, and you can't erase that from their memory when they go through the second part. Can you imagine, for example, if I was testing people's willingness, testing a new therapy to treat depression? So I bring people in who are depressed, and I offer them therapy, talking therapy, I'm a psychologist, for 16 weeks. And I give them this new technique, which I think is dramatically going to reduce their depression. Well, once I put them through that therapy, how am I going to put them through the old therapy and test them a second time? It's just not going to work. So there are some designs that just won't lend themselves to a repeated measures because of practice effects where that you just can't erase or eliminate what's been done to them already. If your variables aren't affected by practice effects, then a repeated measure design can be very helpful. But the bottom line is that now brings us to the end of our discussion of t-tests. So to summarize or put a nice bow on all of these comparisons, we progress from a z-score, where we're looking at an individual's difference from some population parameter. Then we looked at, again, a z-score, where we're looking at a sample of individuals and how that sample differed from a population of interest. However, if we were missing the population parameter of sigma, then we progressed to t, where we are once again looking at the difference between a sample and where they fell relative to a population using an estimate of sigma. But if we were missing even mu from our experiment, and we had to use or introduce a control group, we could once again calculate t, where we compare two sample means instead of a mean and a population mean. And we are looking at, or we compare that to what we would expect between two samples coming from the same population by chance alone. But those are two independent samples. So we had the one sample t-test, we had the two sample t-test, and then we just finished up with an introduction to the paired samples t-test, where instead of having two separate groups that we're comparing, or one group that we're comparing to a population, we're instead testing the exact same individuals under two different conditions and seeing how far apart those two performances were. So that was the progression of Z up through the three different variations of t-tests. Hopefully this was helpful and made sense to you, but as always, let me know if you have any questions. Thank you for your time.